Okay, so I'm Ming-Guang. I'm a postdoc working in Conquin's lab, Harvard Chemistry Department. Here are our group members right now, and red label people directly contribute to the work I will present today. Before I talk about the reactions, I want to mention that making ultracold molecule is hard, and because unlike atoms, the molecule doesn't have a closed optical transition, which makes direct laser cooling challenging. In our lab, we use a different approach. We cool atoms down first, then we associate them into ultracold molecules. And this approach was first demonstrated by this benchmark paper from Debbie Jin and Jun Yi's group. Jun's there. And as mentioned by Jun this morning, Conquin, as the first author in this paper, was a graduate student there. And now it's a PI in Harvard University. 10 years later, the KRB ultracold molecule were reborn in the Harvard University, and we use them to study ultracold molecule reactions in the Harvard Chemistry Department. The basic idea, back to this paper, they have shown that thousands of molecules can be trapped at a temperature about few hundred nanokelvin. The basic, how do they do that? The basic idea can be shown by this cartoon picture. Start from the ultracold mixture of rubidium and potassium atoms. Then you ramp the magnetic field to associate them into a weakly bound molecules. Right after that, you can do a stir-up two-photon process to drive the weakly bound molecule down to the ground state molecules. What remarkable is the whole process involved here is coherent. That means if you do the reverse operation, you can convert all the ground state molecule back to the free atoms. By using the same method, other molecules have been realized by different groups in the world, as shown here, and more is coming. Soon after people realized our very high phase space density of molecular gas, they found that the density of the molecules decay. If you feed the data to a two-body loss model, it fits very well, which suggests that the molecule can react with each other even when they are at absolute ground state and with an extremely low temperature. Since the previous talk, people have compared this collision energy in different units. So here I just convert this temperature in the wave number. So that's just compared with other people. At the early days, people will think about this reaction in terms of the exothermicity. That is, if you draw the energy levels of the two molecular reactants as here, then all the possible reaction channels can be plotted here. For these triatomic reaction channels, their lowest energy already quite high compared to the initial reactants. So those channels are energetically forbidden. So move down to the lower one here, with the forced interaction path. The energy of the product channel can be lower than that of initial reactants. So this process can be exothermal. Or we say this kind of molecules can be chemical reactive. These molecules include the potassium rubidium, lithium sodium, and sodium cesium. Although I only draw the lowest energy level here, there are a series of vibrational and rotational level above these lines here. Alternatively, there are some other molecule species. Their product energy can be higher than that of the initial reactants. So this process is endothermal, or we can say that this kind of molecules are non-reactive. This molecule including the sodium, potassium, sodium, rubidium, cesium. Based on this argument, right, you will say, okay, let's choose the non-reactive molecules. You will expect a very long lifetime of the molecules. After people tried that, they found that the lifetime of these non-reactive molecules are actually quite similar to the KRB case. So, which suggests that the aforementioned picture is not sufficient. For us, our goal is, later people point out that this discrepancy may due to the poorly understand of this intermediate complex. One possible scenario is if the intermediate complex is long-lived, so they probably have the chance to collide with another molecule or scatter a photon from the optical dipole trap that eventually relax to the deeply bound stable states. All this situation can cause the molecule number loss. For us, our goal is to build an apparatus not only allow us to precisely control the quantum states of the initial reactants, but also be able to directly detect reaction products. Particularly, we hope to directly detect this intermediate complex so we can know more about this property. There are three main experimental challenges. The first one is to make ultracold molecules. The second one is we need a high efficiency detection method, which is a photoionization based detection. The third one is a combination of the first two. So in the past 4 years, we have been building this apparatus, and now it's working well. And the optical table on the right, that have all the lasers we need for ultracold items and molecules. And the optical table on the left have our main vacuum chamber and also the photoionization UV pulse laser. So our experimental sequence can be illustrated by this cartoon picture. First of all, we start from dual species mode of rubidium and potassium atoms. Then we magnetically transport them into a vibration chamber to do the RF vibration. And after that, then we load them into a movable optical dipole trap, then transfer the cold item into our chemistry chamber. Over there, we have about 100,000 items at 500 nanokelvin. To make a ground state molecule, we basically follow the same steps as the GLA groups. We do the Feshbach molecule association, then followed by a 2-photon stirrup. And the two stirrup laser we use here is a 690 and 970 nanometer laser. These two lasers need to be phase coherent with each other, so we lock both lasers into a stable cavity here. Those numbers are for experts. And eventually, we have the stirrup efficiency about 92%. And by using the conventional absorption imaging, we detect about 10,000 KRB molecules at temperature about 500 nanokelvin. So we have molecules, we can let them react. To analyze these molecules, we use a UV pulse dye laser to generate two hollow beams, which cross at the molecule location here. The lasers run at 10 Hertz repetition rate, and we tune the wavelengths at 285 nanometer. With this wavelength, we can analyze any molecules we care about. This picture shows a beam profile of our hollow beam, one of our hollow beams, and that's surrounding the trapped molecule here. For the reaction products, once they form, they are going to move out of the shallow ODT, optical dipole trap, then captured by this ionization laser with certain probabilities. After we ionize it, we can turn on our electrodes to repel the ions, fly along a 1 meter long time-of-flight tube, eventually captured by a delay line MCP detector. So here shows our homemade electrodes and also self-assembled delay line MCP detector. The reason why we have so many electrodes here, because we are trying to configure them, works as a velocity map imaging setup. Simply speaking, with this ionization system, we can not only extract the mass information or from the time of flight of the data, but also get the momentum distribution of the ions from the two-dimensional spatial distribution. So I want to mention that here we detect the K plus, RB plus here. So if you look at the momentum distribution, there are two features. So there's the center feature and also the big ring here. So we understand there's a big ring that they are probably from the dissociative ionization of KRB. But for the center feature, we think they are from the leftover items, although we try very hard to clean them up, the same way as other people did. We can still see the leftover items with a very sensitive detection method. Here shows the raw data of our time of flight. To convert them into the mass, we use this mass and time of flight relationship. Then we can convert them into the mass. Then from the mass spectroscopy, we can identify what species they are. If we zoom in the same data set by 300 times, you can see the K2 and RB2 come up. So for us, we further check this signal by comparing them to the ionization background. The color-coded signal are really true here. From there, we see expected signal K2 RB2 ions, and also unexpected signal K2 RB ion and KRB2 ion. Also, we didn't see something we hope to see there. So let's look at the momentum distribution of all these ion signal. First, let's look at the K2 and RB2 that we expect to see. Since we expect them from the ultracold reactions, so their momentum distribution should be very small. If you look at their momentum, indeed, we see very small feature for these two products. And if you draw the yellow dashed line here is represent the largest possible reaction energy here. You can see these ions are still within these circles. Now let's turn to our unexpected ion signal, K2RB and KRB2. From the momentum distribution, you can see they have very large momentum distribution, which may suggest that they are not from the ultracold reaction of KRB. One possible pathway, we think, at the beginning, is this may form some photoionization effect. For example, dissociative ionization of the K2RB2 intermediate states. To verify this idea, we need to know the photoionization information of the intermediate complex. Then we ask the help from one of our theory friends, Olivier Dinu. To our surprise, after a few days, they can send us this ionization threshold calculations. So the intermediate energy we define here as a zero energy here. And as you can see, all these energy, different ionization channels here are dissociative ionization channels. And this one is the lowest dissociative ionization threshold, around 346 nanometer. And this one is energy threshold for direct ionization, around 385 nanometer. As you may notice from all these dissociative ionization channels, we see the K2RB ion and KRB2 ion, which could explain our previous triatomic ion signal. To verify this idea, it would be cool that we can tune our ionization laser wavelengths to directly ionize our intermediate complex. For example, we can choose our UV laser wavelengths 356 nanometer, which is above this direct ionization threshold, but below the lowest dissociative ionization threshold. By doing this, we expect to directly see the K2RB2 ions. Here shows our results And as you can see, K2RB2 ion popped up. If you look at their momentum distribution, indeed, they have very, very small momentum distribution, which is consistent with a zero energy, as we expect. So this is the process we suspect to see what's going on here. And one thing I forgot to mention, to take in this kind of data sets, it takes about a week, 24 hours. Fortunately, we can't do that at the beginning. But if we want to do further the similar data taking, that's not possible. I guess that's impossible. So recently, we updated our UV ionization laser from a 10 hertz to a 10 kilohertz. So that really helped us. So now the similar data sets, we can really, we only need to accumulate for 2 hours. So with this powerful tool, we can really like do some spectroscopy on the intermediate complex. And here shows our recent data, and we do the intermediate ionization versus over different UV laser wavelengths. As you notice here, there are 346. That's the number we expect for the lowest dissociative ionization threshold. Once your wavelength is longer than this, you can see the K2RB2 ions is enhanced. Below that, there's a suppressed. That's consistent with the theoretical calculations. With all this evidence, let me conclude. First of all, we definitely see the K2 and the RB2 reaction products. And also, we think we also directly detect the very short-lived intermediate complex, which is not possible for the ordinary chemical reactions due to extremely short lifetime. But for ultracold reaction, the lifetime of this intermediate can be long-lived. With that, let me outlook. With this new apparatus, we hope to, in the future, we are going to measure the lifetime of the intermediate complex. Also going to do some quantum state resolved detection on the reaction products. Also probing some universal reaction near the quantum to classical transition. Our ultimate goal is to realize quantum control over the reactions. Thank you for your attention.
Questions?
Yes.
So from your, you said you were going to measure the lifetime of the intermediate state, but can you already put like a lower bound on it or something?
Yeah. So we have two ways. Right now, we already from our tetramer that directly K2RB2 ion detection, we can already put some bounds based on the detection efficiency, how much you expect. So that bounds, the lifetime is in between 300 nanosecond and 2 microsecond. But in the future, when we say we want to directly measure, we actually really want to have a way to do some quench, like activate the reaction, then directly measure the K2RB2 ions or intermediate complex, the population coming up with the time. Yeah. Okay.
So just about the number that you just mentioned, upper bound, is that limited by radiative lifetime? Do you know what the radiative lifetime of this molecule?
Radiative, you mean the intermediate complex?
That's right, yeah. So the tetramer, I mean, does it have dipole?
Already have dipole, yeah.
So you would have a radiative lifetime, right? So you can't go beyond that.
Mm-hmm. Yeah.
So would that be a microsecond range, or does anybody know?
Yeah, I never thought about that. Yeah, I don't know.
The radiative is longer, right? Probably on the second day.
Sorry. Whichever.
So, question. So after you rampy ionize this product, you have an ion in your ensemble, which would have much longer range interactions. Is there any concern about secondary reactions with the ions that you create within the rampy?
So we use a one photon ionization. So it's not exactly rampy. Just one photon ionize everything.
Not rampy, one photon ionization, but you have the ion product which could react with.
Yeah. So the pulse is about 10 nanosecond. During that 10 nanosecond, what kind of interaction could cause you haven't? Yeah. Once we ionize them, actually during our ionization right now, our electric field, electrodes already on, so it will immediately repel them, fly away. So I guess we haven't run the calculation to estimate that, but hard to say, yeah. David?
Yeah, so if I understood correctly, the K2RB2 you detect must have been made in the dipole trap and then leave the dipole trap in order to enter your ionization volume.
Yeah, that's
so that
correct.
means there has to be a mechanism that stabilizes the K2RB2. Any speculation about how it is that you can stabilize that? Because if it's just two-body collisions, it shouldn't be able to leave the dipole.
Once they react, the exothermicity about some wavelength big.
Well, that would explain why you would make K2 and RB2.
Mm-hmm.
The tetraatomic.
Oh, you are talking about tetramer.
Yeah.
Actually, one thing I probably forgot to mention, all this tetramer data we actually have a way to tell where it's from the time-of-flight line shape. Yeah, so we think this K2RB2 ion are directly from the in-track, the center, not from the ring. And although I mentioned we are trying to do a hollow beams, trying to avoid deplete the KRB, but there are actually some UV light going on there. Yeah. Actually, when we want to detect the K2RB2, we basically use solid beam instead of the hollow beam. Directly look at the in-track. Yeah.
Any other questions? We have plenty of time now.
Goes faster.
Well, a quick question. So now you have these tools available. You can go to KID, different rotational states, and just directly measure the released energy in K2 or RB2 that would be corresponding to initially putting in the first rotational excited state and so on.
Yeah, that's right. That's one of the plan.
That would be a further confirmation, right? Whether you think is that.
To confirm the.
Like you said, initially when you said rubidium-2 and potassium-2 coming out, they have very low energy, and it's corresponding to basically that exothermic energy release.
Oh, I see.
But if you go to the higher rotational energy, then you will see correspondingly large increase in the energy in the rubidium-2 and the potassium-2.
Yeah. That's one thing we could do. Yeah.
Yeah, and also it will be, who earlier talked about this, also detected this rotational dependence of the reaction rate. So over here, he can do that too. If you prepare it in the rotational excited state and do the same measurement, and I think it will be, the rate will be rotational state dependent. And there will be some new physics in there.
Yeah.
Because even if it's only controlled by the non-range, I think there is a mechanism for the rotational excitation to affect the non-range physics. Any other questions? Yeah, if not, we conclude our afternoon session and see everybody tomorrow. Yeah, let's thank all the speakers.